In this presentation, we will discuss Timoshenko beam theory. Timoshenko beam theory is named after a Russian engineer Stephen Timoshenko, and it is also one of a classical beam theory, is an extension to the Euler-Bernoulli beam theory. The Euler-Bernoulli beam theory assumes that the transverse shear deformation in a beam is negligible. In contrast, the Timoshenko beam theory considers the effect of both bending and shear deformation. Shear deformation becomes very important in beams with high aspect ratio. In other words, if depth to span ratio of a beam is very high, then shear deformation will be significant. The significance of shear deformation was discussed in our previous example of a cantilever beam subjected to concentrated load. In that, whilst deriving the expression for elastic curve of a neutral axis, we found that it had a component related to normal stresses and another component related to shear stresses. It was found that the deflection component due to flexure stresses or normal stresses was the same as depicted by the Euler-Bernoulli theory. However, there was another part which was the shear deflection, and that was dependent on the depth to span ratio. If depth to span ratio becomes significantly higher, then the shear deformation would also become significant. The Timoshenko beam theory actually focuses on shear deformation and tries to bring the shear deformation in the Euler-Bernoulli beam theory. Before getting into the crux of Timoshenko beam theory, let us now refresh our memory about few concepts of elementary beam theory. From the elementary beam theory, we know that slope of the shear diagram is equal to the applied load W, which is uniformly distributed, and also slope of the moment diagram at each point is equal to shear at each point. These expressions were determined by considering a beam subjected to some distributed loading and taking a piece out of that beam and then applying the equation of equilibrium on it. So the equation of equilibrium on this free body would be summation of all the forces equal to zero and summation of all the moment equal to zero. Summation of all the forces equal to zero gave us the first expression, which is the slope of the shear diagram at each point is equal to the applied distributed load intensity, and the summation of moment of this free body equal to zero will give us slope of the moment diagram at each point would be equal to shear at each point. If you want to see this topic at a greater depth, then I would refer the listener to Mechanics of Solid 1 playlist. The second concept which is of interest in the Timoshenko beam theory would be the Euler-Bernoulli beam theory. In the assumptions of Euler-Bernoulli beam theory, we discussed that plane section of the beam remain plane. We discussed Euler-Bernoulli beam theory in the beginning of this lecture series. So the concept of plane section of the beam remaining plane enabled us to determine the axial stress in the Euler-Bernoulli beam theory. In Euler-Bernoulli beam theory, we said that if we consider two vertical fibers which are very close to one another, and before deformation, if they are perpendicular to the centroidal axis, after application of the load and bending of the beam, these two fibers will orient in such a way that the top point A and C will come closer to one another and the bottom point points BD will go further from each other. However, the fiber AB will remain perpendicular to the neutral surface. So, plane section of the beam remaining plane meant that AB, which is straight before application of the load, will remain straight and plane after application of the load. And implicit in this assumption is the idea that AB, after application of the load, will still stay perpendicular to the neutral axis. It was this assumption of fiber AB and CD remaining perpendicular to the neutral surface that we considered AB and the original position of CD, which is written over here C prime D prime, as parallel to each other, and the line OD being a transversal would enable us to make the subtended angle d theta equal to the angle d prime FD. In other words, this concept of the vertical fiber remaining perpendicular to the neutral axis after deformation helped us to use trigonometric concepts for working out the expression sigma 3 is equal to Ex2 by rho. Later, this expression was used to work out the flexure moment capacity. The flexure moment capacity was determined by taking summation of moment about x1 axis equal to 0. That meant that if we consider a small element at a distance x2 from the neutral surface and we take the stress on that element as sigma 33, so we can work out the moment m1 equal to sigma 33 times dA times x2, and then integrating that for the whole cross section and plugging the values of sigma 3, we got m1 equal to EI by rho, or E by rho is equal to m over I is equal to sigma 3 by x2. So this is our famous Euler-Bernoulli theory. The third important concept in elementary beam theory is beam deflections. So as we have discussed, this ratio E by rho equal to m over I is equal to sigma 3 by x2. This ratio will now be used to get an expression for beam deflection. So we consider the same beam as discussed, subject to some loading. If we take 2 points which are very close to one another, draw tangents on those 2 points shown as A and B, and then draw normals to those tangents, they should meet at a point provided that beam has deflected. In the case of small deflection theory, we can assume that if the points are close enough to one another, then keeping O as center, we can draw a circle which will touch the 2 points A and B, and also all the points which are in between A and B. The radius of that circle can be called as a radius of curvature. Since we are dealing with small deflections, AB, which is of length ds, or which is an arc of a circle, can be considered equal to dx. The slope of this elastic curve would be equal to dy by dx, considering x-axis is in horizontal direction and y-axis is in vertical direction. So we can write the slope would be equal to tangent theta equal to dy by dx. Tangent, say drawn at point A, will make an angle theta with the horizontal axis, and tangent of that theta would be equal to dy by dx. If we want to find out exact theta at point A, we will have to put dy and dx value corresponding to point A. In the case of small deflection, we can equate tangent theta approximately equal to theta, and we would get theta is equal to dy by dx. Now, differentiating this equation with respect to x will give us d theta by dx equal to d2y by dx square. As we said that a, b, and o dot can be considered as a sector of a circle, we can write ds equal to rho d theta, or 1 by rho is equal to d theta by ds is approximately equal to d theta by dx, or 1 by rho is equal to d2y by dx square from equation B. Since 1 by rho is also equal to m over ei based on our Euler-Bernoulli beam theory, we can write ei d2y by dx square is equal to m. We can integrate this equation twice to get the equation of the elastic curve. Now we'll come back to our Timoshenko beam theory. We will assume a cantilever beam subjected to some loading, having coordinate axes at the free end of the cantilever, x1 being horizontal and x2 vertical. Thus, we will try to derive the concepts we just discussed, such as the shear moment and the applied load relations, Euler-Bernoulli beam theory, and deflections in elementary beams with respect to x1 and x2. So in the case of this cantilever, we can write the internal forces equal to shear and moment. This direction of shear and moment is considered as positive in our elementary mechanics. Based on these directions, as we said, that dv by dx is equal to the distributed load intensity, and the slope of the moment diagram at a point is equal to the shear at a point, we can write m dash, which is dm by dx1, is equal to shear, and the slope of the shear dv by dx1 is equal to the load intensity at that point. We can also denote the deflection small v equal to u2 x1 0. This means to say that v at a particular point along the beam in x1 direction would be equal to the displacement u2 at that point in x1, keeping x2 equal to 0. In other words, v can be considered deflection of the neutral axis. If we differentiate v with respect to x1, we should get tangent beta. As we discussed, tangent theta was equal to dy by dx. So in the current case, if our vertical deflection is v, then differentiating that with respect to the horizontal axis, which is x1, we should get beta, and that beta is approximately equal to beta. Thus, beta is equal to partial v by partial x1, or v dash is equal to beta at any point in x1. So this expression is similar to what we discussed over here. Another important term is that u1, which is the displacement in x1 direction, will be equal to minus theta times x2. So in this case, if initially we had two fibers A, B, and C, D, after deformation, these fibers got oriented and they were making angle d theta with their original location. So the extension hk shown over here is actually the axial displacement along the longitudinal axis of the beam. Therefore, u1 is the displacement along a fiber in longitudinal direction equal to theta times x2. The reason we are taking negative in this expression is that our fibers below the neutral axis are considered to be in the negative x2 directions. We can differentiate this expression u1 is equal to minus theta x2, and we will get u1 comma 1 is equal to minus theta prime x2. Since the axial strain in the fiber in x1 direction would be E time strain 1, and strain 1 according to our strain tensor is equal to U1, comma 1, and also in accordance with the Euler-Bernoulli beam theory, our axial strain in the longitudinal direction is equal to E times x2 by rho. Please note that x3 in this case is taken in the longitudinal direction. However, in here we are taking x1 in the longitudinal direction of the beam. Therefore, we can write, as per the Euler beam theory, sigma 11 is equal to minus mx2 over I. Plugging the values of u1, comma 1 as per this expression, we would get E times minus theta prime x2 is equal to minus mx2 over I. Thus, we would get theta prime is equal to m over EI. So there are two important things to note in the Euler-Bernoulli beam theory. One is plane section remaining plane. So the implication of this assumption is that we get the expression u1 is equal to minus theta x2. And the second implication is that we get theta prime is equal to m over EI. As we discussed in our engineer's beam theory assumption that plane section of the beam remains plane, and also that the vertical fiber after deformation will remain perpendicular to the neutral axis. Thus, the angle subtended by this arc will be equal to the angle d prime fd shown in this figure. Thus, the d theta, which is the angle subtended by this arc, is equal to d theta, which CD makes with its original position. That means to say that the vertical fiber CD is perpendicular to the neutral axis. Therefore, this theta, as per Euler-Bernoulli theory, would be equal to beta. Or in other words, V bar will be equal to theta. So these two are the basic assumptions of Euler-Bernoulli beam theory. However, coming to now Timoshenko beam theory, if we consider shear deformation of the beam, it will try to destroy this second assumption. So if we have got a beam which deforms in shear, if this is the neutral axis, in case of shear deformation, a square section will become rhombus section. Thus, before application of the load, if the vertical axis was orthogonal to the neutral axis, after deformation, this orthogonality is disturbed due to shear deformation, and we have the vertical axis oriented at some angle alpha with respect to the neutral axis. So that's shown over here also, that due to the shear deformation, this vertical fiber orients at an angle alpha with respect to the neutral axis. So in order to discuss Timoshenko beam theory, it is important that we relax this assumption, which is theta is equal to beta. So let us reiterate what we have discussed so far and how would we proceed. We have said that applied load W is related to V, and V is related to M, and that is via the slopes. So slope of shear at a point is equal to the distributed load magnitude at that point, and slope of the moment diagram at a point is equal to the shear magnitude at that point. And this will always be true because this is derived based on the equilibrium. Equilibrium has to be satisfied all the time. The other relation is theta prime, which was equal to m over ei. We can integrate theta prime to get theta, and then according to Euler-Bernoulli theory, this theta is equal to beta or theta, and the vertical deflections are related by this relation theta is equal to v prime. So using this relation theta is equal to v prime, we can integrate this and find the final vertical deflection in the case of Euler-Bernoulli beam theory. We can draw the solution diagram as shown over here. If we have theta triple prime, we can integrate that and get theta double prime. And we can integrate that further and we can get theta prime. And integrate that again and we will get theta. From theta, then we can determine our vertical displacement as we have discussed over here. Since theta is equal to v bar and that we have derived, so we can write theta is equal to v bar. Theta bar, which is actually d2 theta by dx square, that is equal to m over ei. And we said that d theta by dx is equal to d2y by dx square, and that was equal to m over ei. So based on this derivation, we can write theta prime is equal to m over ei. Since m prime is equal to the shear magnitude, so we can differentiate that once more and we will get v or ei or shear. And differentiating this once more will give us the magnitude of the load w or ei. So theta triple prime is equal to w or ei. Now all what we have said is true for Euler-Bernoulli theory. If we want to use the Timoshenko beam theory approach, we have to relax small v prime is equal to theta. The rest of the relations are all applicable as they all involve equilibrium and also they are based on plane section remaining plane. So Timoshenko beam theory also assume plane section remaining plane. The only place where Timoshenko beam theory differs from the Euler-Bernoulli beam theory is that it doesn't consider the vertical fiber after deformation remaining perpendicular to the neutral axis. So we have to come up with a new strategy to get our deflection from theta. We can't use theta is equal to small v prime. That's why we have written that plane section will remain plane in Timoshenko beam theory, and plane section do not remain perpendicular to the neutral axis. That is, theta is not equal to beta. So we have to update this solution, and the way we can update this solution is by resorting to our shear expression. We said that our shear deformation is equal to u1, 2 plus u2, 1. So that expression has been written over here, remembering that gamma 1, 2 is equal to 2 times epsilon 1, 2. So 2 epsilon 1, 2 is equal to u2, 1 plus u1, 2. Since u1 is equal to minus theta x2, so that is still valid. u1 is equal to minus theta x2. We can plug the value of u1 in this expression. Epsilon 1, 2 is shear. If we assume that epsilon 1, 2 remains constant along the whole depth x2, then we can write epsilon 1, 2 is equal to half beta minus theta. So u1 comma 2 will give us minus theta. u2 comma 1 is beta in our case, and epsilon 1, 2 we have written as it is. But in this we have assumed that epsilon 1, 2 is constant along x2. So shear deformation is constant along the whole depth. As we know, sigma 1, 2 is equal to 2 mu epsilon 1, 2. And this we derived earlier. In our plane strain and plane stress problem, we derived the constitutive equation. Sigma alpha beta is equal to 2 mu, big bracket, epsilon alpha beta plus the expression involving W and epsilon 1 plus epsilon 2, 2. Now, in the case of shear, since when alpha is not equal to beta, this chronicle delta will nullify this second term and we will get sigma alpha beta is equal to 2 mu epsilon alpha beta. So that is true for both plane stress and plane strain problem. Thus, we can write sigma 1, 2 is equal to 2 mu epsilon 1, 2 or is equal to mu beta minus theta. Now, V, which is defined as shear, is equal to minus integral of sigma 1 to dA. The reason we have taken V as negative is that as per our sign convention, normally the load is applied in the opposite direction. So the shear will be negative. If sigma 1, 2 is considered constant along the whole depth, then sigma 1, 2 can come out of this integral and we will get sigma 1, 2 times A. Thus, we can write sigma 1, 2 equal to minus V by A. Plugging the values in this expression, we get theta is equal to beta plus V by mu A. As we discussed earlier, that beta is equal to small v prime. So plugging the values of v prime over here, we get v prime is equal to theta minus v by mu a. So using this expression, we can find out our shear deflection. So this is now our new relation between v bar and theta. Previously, we took v bar equal to theta. Now it has got another factor which takes shear into account. However, this expression will also raise some eyebrows because as we know, shear on the cross section is never constant. It varies parabolically as tau is equal to VQ by IB and shear is varying parabolically within the cross section. So therefore, the assumption that the shear is constant is not valid. That's what has been written over here. Sigma 1, 2 is not constant and sigma 1, 2, which is a function of x1 and x2, is equal to minus VQ by IT, T being the width of the cross section. So instead of developing a strategy which will consider sigma 1, 2 varying along the cross section, we introduce a correction factor k in our equation so that k removes the inconsistency in the shear. Now, as we know, capital V, which is shear, is equal to EI theta double prime. Please note that capital V is shear and this small v prime is actually the rate of change of displacement with respect to x1. So on the left hand side, we have got this small v prime. On the right hand side, we have got this capital V, which is shear. We can plug value of capital V, which is EI theta double prime, and we get theta minus EI theta double prime by K mu A. If we call this theta double prime as theta by L square, so we can plug value of theta by L square in this expression. So in other words, this theta double prime can be approximated as an order of magnitude. So theta double dot can be approximately equal to theta by L square, L being the length of the beam, would come out to be V prime is equal to theta minus small bracket 1 by k EI by mu A L square. This factor E by mu I by AL square can be called as gamma, and this gamma factor can be worked out for different cross sections, such as gamma would be equal to E by mu small bracket h by L whole square for a rectangular beam having depth h and width t. This factor gamma comes out to be a function of h by L, or depth by length, which will become smaller if h by L tends to 0. Thus, h by L is called the shear influence factor, and this is the same factor which we considered in our cantilever beam problem previously. Now let us try to revisit our cantilever beam problem and implement the Timoshenko beam theory. So we have a cantilever beam of length L having load P applied at the free end. The coordinate system is similar to what we did before, x1 along a horizontal axis, x2 along vertical axis, and the origin at the free end. The cross section of this cantilever is shown in this figure. So the depth of the beam is h and the thickness of the beam or width of the beam is t. So our aim in this question is to implement the Timoshenko beam theory and work out the deflections. Let's remind ourselves of this solution diagram. We discussed earlier that theta triple prime is equal to W over EI, theta double prime is equal to V over EI, where V is the applied shear, W is the distributed loading, then theta prime is M over EI, and theta is related to V prime by this Timoshenko formula, which is V prime is equal to theta minus V by K mu A. Please note that this V prime is the vertical deflection and this capital V is actually the applied shear. So we can draw the free body diagram of this beam. We will have the shear facing down and a counterclockwise moment equal to minus Px1. The shear will be equal to minus P according to our sign convention. So in this solution diagram, we can either start from theta triple prime equal to W over EI, or we can start from theta double prime is equal to V over EI. W in our cantilever case is 0, so therefore we can write EI theta triple prime is equal to W is equal to 0, and since there is no distributed load applied on the beam, we can have EI theta double prime equal to V, and which is the applied shear, and that is equal to minus P according to our figure. Now we can integrate this equation and we will get the moment equation. EI theta prime is equal to M, which will be equal to minus Px1 plus C naught. So if we integrate our theta double prime, we will get theta prime, and at the right hand side we will have M over EI. So moment is equal to minus Px1 plus C naught. We can find out our C naught now by using the boundary conditions, and the boundary condition can be at x is equal to x1 equal to 0, moment is equal to 0. So that will give us C naught equal to 0. We can integrate this equation once more and we will get, in terms of rotation, EI theta is equal to minus P by 2 x1 square plus C1. Please remember that as per our previous discussion, theta was actually the orientation of the vertical fiber and beta was the angle subtended between 2 points on the elastic curve. So again, we can put conditions that at x is equal to L, our rotation theta is equal to 0, and we will get C1 equal to P by 2 L square. Thus, we will get a general equation of theta x1 P by 2 EI L square minus x1 square. So essentially, in our solution, as per our solution diagram, theta triple prime, theta double prime, and theta prime, these are all the same regardless whether we are using Euler-Bernoulli beam equation or Timoshenko beam theory. The difference comes when we relate our theta with small v prime and v being the deflection of the beam. So it's there where the difference lies. So the step 2 of this problem is to find out the deflections. As per our engineer's beam theory or Euler-Bernoulli beam theory, our v prime is equal to theta. So we can write v prime is equal to p over 2i L square minus x1 square, and we can integrate this equation. We will get p by 2 ei small bracket L square x1 minus x1 cube by 3 plus c2. Now we can impose another condition, which is the displacement at x1 equal to L is equal to 0, and that will give us C2 equal to minus PL cube over 3EI. And from there, we will get the equation of our elastic curve, which would be PL square over EI, big bracket, half, small bracket, x1 minus x1 cube over 3L square, minus L by 3, big bracket close. So according to Euler-Bernoulli beam theory, at x1 is equal to L, we have no horizontal, vertical, or rotational movement. So our elastic curve at the neutral axis will remain rigid at that point. So that is an important observation in the case of Euler-Bernoulli beam theory. Now, what will happen in the case of Timoshenko beam theory? So again, we have V prime equal to theta minus V or K mu A. This is as per our Timoshenko beam equation, which is V prime is equal to theta minus capital V by K mu A. So rewriting this equation and plugging the value of theta, which is P over 2 EI small bracket L square minus x1 square, and we will get capital V, which is shear, and that is minus P in as per our sign convention. So we will have plus P or K mu A. Now we will follow the same procedure as in Euler-Bernoulli beam theory. We integrate and we get P over 2 EI small bracket L square x1 minus x1 cube by 3 plus P over K mu A x1 plus C2. So again, imposing the condition displacement at L is equal to 0, and that will give us C2 equal to minus PL cube over 3EI minus PL or K mu A is the area of cross section of the beam. So essentially, we will get our equation of the elastic curve equal to PL square over EI, big bracket, half, small bracket, x1 minus x1 cube over 3L square minus L by 3 plus 1 by K EI mu A L square into small bracket, x1 minus L and big bracket close. As we said earlier, that we can call this constant E over mu H over L square as gamma in the case of a rectangular section. So using gamma, we get deflection at x1 is equal to 0, which is the free end, equal to PL cube over 3EI 1 plus 3 gamma by K. Thus, Opening the bracket, we get PL cube over 3EI plus gamma by K PL cube over EI. And this first term shows the contribution of moment, and the second term shows the influence of shear. So this is similar to our analytical equation which we derived in the case of cantilever beam. We had a contribution of bending, and then we have contribution of shear. So the same thing is true in this case. Now let us compare our final result, especially at the root of the cantilever. So as per our Euler-Bernoulli beam theory, if we find the slope of the elastic curve at the root, we would get 0. So in other words, at the root, the neutral axis doesn't rotate. However, in the case of Timoshenko beam, the slope of this elastic curve at the root doesn't come out to be 0. In other words, it comes out to be P by K mu A. So that is consistent with our assumption that in the case of Timoshenko beam, our vertical axis or the vertical fiber is not perpendicular to the elastic curve. It is inclined at some angle. And as we can see in our Timoshenko beam, the slope of this elastic curve at the root is not 0. It has moved by a certain angle. So that is an interesting observation, and it clearly tells us that Timoshenko beam is an improvement of Euler-Bernoulli beam. In most of the structure softwares, we can have an option for either using Euler-Bernoulli beam element or a Timoshenko beam element. So we have to use then our engineering judgment whether shear can be appreciable to an extent that the vertical fiber of the beam won't be perpendicular to the elastic curve, or flexure influence is significant, in which case the vertical fiber of the beam will be perpendicular to the elastic curve. Now, one thing we would have realized in our Timoshenko beam that there is a factor K appearing, and this K we introduced due to the error caused by our assumption that the shear is constant along the cross section. So K essentially is the shear correction factor. Now let us have some brief discussion about this K. Before going deeper into K, it is important to remind ourselves of the exact solution which we got by solving our cantilever beam, which was subjected to vertical load. So we use theory of elasticity to get our U1, U2, and theta. We call this solution as an exact solution because it is using theory of elasticity. It hasn't got any restriction like plane section should remain plane. Therefore, it is a more refined solution of Euler-Bernoulli beam theory. The solution given by this problem is better than Timoshenko beam theory because in the case of Timoshenko beam theory, we still assume that plane section remain plane. So that assumption was not dropped. It was in the case of Timoshenko beam theory. It was the assumption of plane section remain perpendicular to neutral axis, which was relaxed. Hence, the analytical solution by theory of elasticity is more exact than both the Timoshenko beam theory or Euler-Bernoulli beam theory. So if we rewrite our U2 equation of our exact solution or the analytical solution using theory of elasticity, we will get Vx1 is equal to PL square over EI big bracket half small bracket x1 minus x1 cube over 3L square minus L by 3 plus gamma 4 by 3 small bracket x1 minus L. At x1 equal to 0, which means the free end, we will get PL cube over 3EI big bracket 1 plus 9 over 4 gamma. Please note that we have introduced gamma in our exact solution. previously we didn't define gamma in our U1, U2 equation. The reason we have defined gamma in this equation is to have consistent result as compared to Timoshenko beam theory, and then from there we will deduce the value of K. So the exact solution is U2 x1 0 is equal to small b x1 is equal to PL square over EI big bracket half small bracket x1 minus x1 cube over 3L square minus L by 3 plus gamma by 4 by 3 small bracket x1 minus L big bracket close. The value of delta or the deflection at the free end will be equal to Vx1 equal to 0. It is negative because as per our sign convention, the deflection of the free end is in the negative x2 direction. Thus, the deflection will be equal to minus V of 0 is equal to PL cube over 3EI 1 plus 9 by 4 gamma. So opening this bracket, we will get PL cube over 3EI plus gamma by 4 by 3 PL cube over 8EI. This is the shear dominant factor, the second term. And in here, we have 4 by 3. So if we put K equal to 4 by 3 in our Timoshenko beam, we will get exactly the same answer as given by the analytical solution or theory of elasticity. Similarly, we can find the slope of our exact solution at x1 equal to L, and we will get P by 4 by 3 mu A, which is not equal to 0. So this also demonstrates that the answer given by Timoshenko beam theory for the slope of the elastic curve at the root of the cantilever is the same, provided K is equal to 4 by 3. Thus, our deflection and the slope of the elastic curve at the root will be equal to the Timoshenko beam theory if we put K value equal to 4 by 3 in our Timoshenko beam theory. However, if we try to find out the energy within the system or the energy at the free end, we will see that it will not match. The Timoshenko beam theory will not match with the exact solution. For K value equal to 4 by 3, we will have to use K is equal to 5 by 6 in order to match the shear energies. So one thing we can conclude that the Timoshenko beam theory gives us more exact solution as compared to engineer's beam theory. And if we use appropriate value of K in our Timoshenko beam theory, then it's possible that we get close answer to the exact solution from the theory of elasticity.